Now we can begin our problem from here itself, but let us use some template. We have well-defined template for electrolyte system. Let us use it because there are certain advantages of template, because in the template certain components are predefined, because in electrolyte system, say water as a solvent is a certainty. So some components, some property methods, they are already inbuilt in the template. Okay, you do not have to define them until and unless you have some specific purpose to change. Okay, and also we can use certain wizard or electrolyte wizard. And the purpose of wizard is they can bring in the relevant reactions based on what are the components that we define in our system. Okay, so we have to identify the relevant components and reactions that are required for our system, and rest of the components and reactions we can delete and we can move forward with our simulation. So that is the advantage of wizard. So we will take the advantage of the template and its wizard and do the simulation. Let us learn that. So for that, let us open a new simulation with the template. So there is a new simulation with electrolyte with metric unit. So let us use electrolyte template with metric unit. So open the selected template. So do we want to close the current run? Yes, I want to close and I do not want to save it. Yes. So the template is open, and as expected, water is already added into the component list because presence of water is a certainty in the electrolyte system. What else is there? We have method. Okay. We have method specification as elec_nrtl. What is elec_nrtl? Elec_nrtl method is electrolyte NRTL model with Redlich-Kwong equation of state for aqueous and mixed solutions. Okay, NRTL you know, right? NRTL is non-random to liquid, and elec_nrtl is a special type of property method dedicated for electrolytes. And there are certain variations of elec_nrtl. For instance, we have eNRTL-HF, that is electrolyte NRTL model with HF equations of state for mixed solvent application. Then eNRTL-HG, that is electrolyte NRTL model with Redlich-Kwong equation of state, uses Hell-Jason model. HG means Hell-Jason. Okay, Hell-Jason model. Then it is unsymmetric electrolyte NRTL model, and this is symmetric electrolyte NRTL model. We will understand what is unsymmetric and symmetric slightly later. So these are the variations of electrolyte NRTL model. Interested readers can go to the help file to learn it better. For the purpose of this problem, elec_nrtl model is useful, so we will stick to elec_nrtl model. And based on what components we give, the solution chemistry will be defined accordingly. So let us go back to our specifications, and we have to add the components, right? So these are the components: vinyl chloride, 1,2-dichloroethane, HCl, acetylene, and later we have to add NaOH also, right? So these are the things that will be needed. So first let us take vinyl chloride and find, as we do not know what should be the compound name. Yeah, so this one. So this is vinyl chloride. So we can just name it as V vinyl fluoride, we can rename it. Okay. And then what else? 1,2-dichloroethane, right? So we just copy and paste and find now. This one. Okay. So let us rename it as 1,2-dichloroethane. Okay. And then HCl acetylene. HCl we can just enter just like that. It will identify itself. And acetylene, obviously we have to find acetylene, find now. There are so many options. Let us go down. Yeah, we have over here C2H2. So let us use a C2H2. Yeah, acetylene. And what else? After acetylene, we have NaOH. Okay. So NaOH also is a straightforward case. Right. Sodium hydroxide will be the component name. So we are done with that. Now the job of wizard comes. You find over here elect wizard. So this is electrolyte wizard. Just press it and it says welcome to the electrolyte wizard. The quickest way to generate components and reactions for electrolyte system through the following steps. Define the base components and select reaction generation options. Remove any undesired species or reactions from the generated list, because generated list will be quite comprehensive. You may not need all the components that has been generated. So you can just delete the unnecessary components and associated reactions. Selection of simulation approach for electrolyte calculation, and review the physical properties, specification, and modify the generated Henry components and reactions if needed. Okay. So these are the standard processes and steps that are generated. Now we have to select two things. One is the chemistry data source and the reference state of ionic components. Chemistry data source, the default is APV14 Aspen Plus version 14.0 reaction. So this is the only chemistry data source that we have. But if you add any other data source from anywhere else, then those options will also come over here. We have not taken anything. We have just brought in the template, and the template is having only this data source. But obviously, if you have some customized data source from anywhere, that also options may come if you add it at the proper place. Reference state for ionic components. There are two options, unsymmetric and symmetric. Now, let us see what they are. The activity coefficients for ionic components are calculated based on either unsymmetric or symmetric. Unsymmetric means we will assume that there is an infinite dilution of the solute in pure water. That means suppose you have small amount of NaCl, you have huge amount of water, so that it becomes an infinite dilution of NaCl in water. So that is the unsymmetric case. And the symmetric case is opposite, where there is no water, only the molten state of the salt, NaCl purely fused. Okay, there is no water, only molten state of the salt. So which one we'll use over here? We know already water is present in the system, so we have to use the unsymmetric one. So we are using unsymmetric. Press next. Okay. Now we have to select the base components and the reaction generation option. Now already we have H2O that is selected as the base component or the solvent. We have to add two more components, that is NaOH and HCl, because we expect that HCl and NaOH, they will react. And then hydrogen ion type. There are two types, hydronium ion or hydrogen ion. So based on which one you choose, the reactions will be generated accordingly. Suppose if you choose hydrogen ion, then you will have a reaction of this nature. Okay. Whereas if you choose hydronium ion, then possibly you will have this kind of reaction. Okay. So it is up to you which type of hydrogen ion that you want to work with. So choose accordingly. And the options for including salt formation, water dissociation reaction, ice formation, you have to tick the relevant ones. Now, ice formation is not needed over here because in our system, the temperature and pressure, they are 25 degrees centigrade, 1 bar pressure. At that point, the ice formation will not happen. So let us neglect these things. So let us keep whatever it has come as default. Press next. Yes. The moment we press next, the salts have been generated. So they say that we have NaOH solid. Okay. So this salt we can neglect because we do not think we will get any NaOH solid because it is only 0.2% of NaOH that will be there in water. So why do you think that it will precipitate? Okay. It is almost infinite dilution. So this one we can remove. And this one also we can remove. Okay. NaOH, anything related to NaOH we'll remove. And the moment we'll remove NaOH, suppose if we remove this one, NaOH to Na plus and OH minus, this reaction will go. Only this reaction will remain. This NaOH is conventional, right? This NaOH is conventional because this NaOH is there in the water solution. But we do not have any solid. So we'll just remove it. The moment we remove, this one will go and that particular solid reaction will also go. Similarly, if we remove this one, this will go and this reaction will also go. So we just remove it. Okay. They vanish over here. Now you see, we have only the relevant salt and their reactions. Okay. Now they have been generated by Aspen Plus. You didn't have to write them through. Okay. Actually, they are the useful reaction, and here also you can find that they have generated hydronium ion. They are not generating H plus ion over here. Okay. So you continue with it. Set up the property with elect NRTL property method. Now press next. Here, simulation approach should be either through the true component approach or the apparent component approach. Now, to understand this, we have to go to the help file of Aspen Plus. Just consult the help file of Aspen Plus. What are the apparent component and true component approaches? For instance, here there are 4 ionic reactions. Water is dissociating in hydronium ion and OH ion. NH3 plus water, that is producing ammonium ion and hydroxyl ion. Similarly, the hydrogen sulfide is producing HS ion and hydronium ion. And hydronium ion And HS ion with water is producing again another hydronium ion and S double minus ion. Right. So there are 5 ionic species thereby produced from this aqueous ionic reaction. All components in this reaction exist at chemical equilibrium condition and are the true components of the electrolyte system. So they are all true components of the electrolyte system. So what are the true components over here? This one, this one, this one, this one, and this one. All 5 are true components. So there are these 5 ionic species, all of them are true components of the electrolyte system. And what are the apparent components? The apparent components, or they can be called parent component also. It is apparent or parent, because from these parent components only these true components have come. So apparent components are H2O, NH3, and H2S. Okay. So from parent component, all the ions are generated. So ions are true components of the electrolyte system and parent components are H2O, NH3 and H2S. So how to choose the true component or apparent component approach? Now this apparent component approach in vapor-liquid equilibrium implies the vapor-liquid equilibrium is solved in terms of apparent components only, whereas liquid solution chemistry in the liquid is solved in terms of true and apparent components. Because vapor-liquid equilibrium, we cannot expect the ions to go to the vapor state, right? Ions never go to the vapor state. Ion is only on the liquid state or dissolved state. So whenever there is a vapor-liquid equilibrium, we know that we have to use apparent components only. But the moment liquid solution chemistry comes, all the true and apparent components come. Okay. And there are certain units which do not support the true species electrolyte chemistry. For instance, the distillation, the petrofrac, okay, extract, equilibrium reactor, Gibbs reactor, they do not support the true species. Basically, whenever we have some solution chemistry that involves electrolytes, we can use true component approach. Otherwise, we have to use apparent component approach only. Anyway, you can just go through this help file to learn more. We'll go back to this and let us use the true component approach. So we can review the Henry component and review the chemistry. So review the chemistry. See, there are 4 equations they have generated. Okay. Now this chemistry we have not provided. I mean, this equilibrium, salt, dissociation, did we enter them? No, we have not. Aspen Plus only generated these equations. So the first equation is HCl plus water producing hydronium ion and chloride ion. Okay. Second is H2O dissociating in hydronium and hydroxyl. Right. Then salt formation. NaCl salt is dissolving into Na plus and Cl minus. It is solid. NaCl is solid. NaOH, it is dissociating. NaOH, it is not solid NaOH. It is conventional, which is dissolved in water. So that NaOH, it is dissociating into Na plus and OH minus. So these are the reaction stoichiometry that we have. Okay. And these are the equilibrium reactions. For instance, this one, equilibrium reaction, the A, B, C, D of the equilibrium constant has been given. So what is the value of A, B, C and D? Okay, T in Kelvin, obviously the equilibrium constant depends upon the temperature in Kelvin, absolute temperature. So the values of A, B, C and D, they have been given by Aspen itself. Aspen has dug out from its database to produce these for you. But concentration basis we have to change from mole gamma to mole fraction. I do not know why it has given to mole gamma. It should be mole fraction only. Okay. And hydrate check. What is hydrate check? There are two options, rigorous and approximate. So this is about hydrate check. Now, while determining which hydrate to precipitate, suppose we have multiple hydrates, including the anhydrous form. Now, for salt precipitation, we have to define which salt or which hydrate will precipitate. Okay. For that, there are two approaches. One is rigorous, one is approximate. In rigorous approach, the Aspen plus property will perform the gives free energy minimization. Then they will understand which one to select. So that is the rigorous one, to find out through gives free energy minimization. But approximate is just to check the lowest solubility product value at that particular system temperature. So this is an approximate one. So which one is having the lowest solubility product value at that temperature? You can select that particular hydrate. Okay. So this is an approximate calculation, and through the gives free energy minimization way, it is the rigorous calculation. So we have to choose accordingly. Now in this system, they have chosen rigorous way of calculating. Okay. And then review Henry component. Now for a dilute solution, they have chosen this to be Henry component, HCl. Keep it just like that and finish. Okay. So we have defined up to NaOH, but all these components Aspen Plus has dug out itself from the database. So hydronium ion, Na plus ion, NaCl solid, Cl minus, OH minus, all of them Aspen Plus has brought in for you. Chemistry. So the list of chemistry, which we have just now checked, so they have been given. Now let us run the property method. So inertial, okay. So electrolyte pair, these four has to be done. So one by one you check it, press next, again press next. Okay, now you can run. Right. So the results are available, property method has been run. So all set, now we can go to the simulation. Now in the simulation, as I said that we do not have to use any columns for that, radfrac and all. Only a simple separator with flash 2 will serve our purpose. So we just bring in a flash 2 over here. So let us name it as a water absorber. And another one we will place over here, that is NaOH absorber. Okay. So we name them accordingly. So this is our water-based absorber. This is our NaOH-based absorber. Now we shall feed in the gas. This is gas stream, and this is pure water. Okay. And this will be, say, first wash liquid, wash 1, and this one is the outlet vapor from the first absorber, which will go into the second absorber, right? So let us write gas 2, and this one is NaOH solution. This one is, say, mostly NaCl solution. Okay, we are expecting NaCl to form over here, and this is the clean gas, right? So we'll name it as clean gas. So this is the gas. Water is being poured from here, getting absorbed. This is wash 1. We'll have most of the HCl over here. Gas 2 going into the NaOH absorber. They are reacted with NaOH. NaCl solution is formed and clean gas is coming out. Okay. Now first we'll set up the gas property. What are the gas property? Let us see. 10,000 kg completely vapor, 1.5 bar. So it is completely vapor. So vapor fraction 1 and 1.5 bar. Okay. Mass flow rate 10,000. And we have taken the mass fraction. Mass fraction 5% HCl, 5% acetylene. So HCl 0.05, acetylene 0.05, and then 10% 1,2-dichloroethane, it is 0.1. So total 0.2. Rest is vinyl chloride. So vinyl chloride should be 0.8. That makes it 1. Right? So gas stream has been set. Then water stream. Water stream is 5,000 kg pure water, 25 degrees centigrade, 1.5 bar. So 25 degrees centigrade, 1.5 bar, and 5,000 kg. Right? So water given, and then NaOH solution over here. So NaOH 0.2%. Now total is 500 kg, 25 degrees centigrade, 1.5 bar. So 25, 1.5 bar, and 500 kg per hour. Then 0.2% NaOH. So NaOH should be 0.002, and rest is water, 0.998. Okay. Okay, it should be mass fraction, right? This is mass fraction. Did I do any mistake in other one? Gas mass fraction. And water. Okay, all of them are set. Now let us check the blocks. So block input. So the sodium hydroxide absorber This second scrubber operates at 1 bar pressure with 0 heat duty. So we have to set heat duty 0 and 1 bar pressure. Whereas the other scrubber, the first scrubber, water scrubber, operates at 50 degrees centigrade and 1 bar pressure. So it is 50 degrees centigrade and 1 bar pressure. Okay, so that makes all the required input complete. So let us check whether we have missed out anything. 5000 kg. No, it's okay. So we have given all the information. Okay, so our required input is complete. Now let us run the process. Yeah, so the results are available now. So we can see the results. Let us check the result summary and the stream. So let us check the mass flow rate. Yeah, so the gas contained 500 kg per hour of HCl, out of which only 0.985579, this much HCl remains in the gas 2. So this is the gas flow rate, this is gas 2 flow rate. So gas 1 is having 500 kg per hour of HCl and gas 2 is having 0.985579 kg per hour of HCl. So majority of HCl has been removed by the first absorber. Okay. And then the second absorber takes in the gas 2 and NaOH solution reacts with that. And the clean gas, let us see how much HCl clean gas has. This is the clean gas. Clean gas is almost HCl free. 10 to the power minus 6 means you can take it 0. Now you can check where that HCl has gone. Okay, HCl, majority of HCl is there in wash 1. Okay, wash 1 is coming out from here and it is having majority of HCl in the form of ion. So here you see 260 kg per hour of hydronium ion and 485 kg per hour of chloride ion. So majority of chloride ion and hydronium ion are there in this wash 1 stream. In between all the mass balances of true components and apparent components, they take place. And you can see the mass balance. You can just do some algebraic calculation. You can arrive at the correct result. Okay. Now this was a very small and useful example of an electrolyte process, and you know how to handle various types of ions, how to use the template and elec wizard to arrive at various equations of your need. Okay, and I hope you have learned many things in this lecture. So we come to the end of this lecture and we'll come back with yet another interesting lecture very soon. Till then, thank you and goodbye.